Alrighty, buckle in. It's Organic Chemistry Chapter 4 about organic reactions. This is a hefty chapter, and you will see at least two passage questions about organic reactions. Whether you will see a full 3 or 4 within one passage, or you will see them in different occasions. The SN1, SN2, and the redox, and asking about the oxidation states and the oxidizations will come in handy if you know about them. So starting off, we have the acid-base definitions. If you recall, Lewis acid accepts electrons and Lewis base donates the electrons. Bronsted acid donates the proton, and Bronsted base receives the proton. Now, we also have Arrhenius definition, but that is very outdated. It only talks about whether if you put it into H2O, it's going to form H3O. That means that it's a acid, and if you put it in H2O and it forms OH instead, then it's a base. But that is outdated because we know there are complex reactions that could go on, such as double bonds and different bonding orders. Now we have pKa can be calculated using negative log of Ka, just like how pH can be calculated using negative log of H, and we can find out using the ratio of proton and the base over the conjugate acid. That is the ratio of base to acid. Okay, next we have nucleophiles. And nucleophiles are defined to have lone pair electrons or pi bonds, and they want to participate in new bonds. They like nucleus, so they want to think about electrons. Electrons love nucleus, right? So they like the positive charges, so they carry negative charges or want to bond. So you have lone pairs electrons here, you have pi bonds on here that can go participate in new bonds, and you have lone pair electrons here. It can also be nitrogen and any other atom that are electronegative, or no, they are looking for protons. They carry a high electronegativity. The stronger the nucleophile typically has a stronger electronegativity. However, there are things called solvents that help with the reaction, and depending on whether it's polar, has hydrogen bonds contained with the solvent or not, it could affect the nucleophilicity. Nucleophilicity strength could increase or decrease. Typically, the more electronegativity, the better the nucleophile, right? However, on a periodic table, if there is hydrogen bonds within the solvent, such as H2O, carboxylic acid, then they donate the protons to certain bases in these nucleophiles and make them decrease in strength the more electronegative they are, because if they're very electronegative, the extra protons bond to them and prevent them from being nucleophiles, active nucleophiles. So think of the H bonds in the polar protic solvent acting as electrophiles and taking away these nucleophiles. So they're kind of like in biology, you have these enzymes and these enzyme inhibitors, right? They're like the inhibitors that compete and take away these extra enzymes that could participate in a reaction. Next, we have aprotic solvent, which don't contain any hydrogen bonds, and their nucleophilicity strength goes up the further up the table you go. So because there are no hydrogen bond in there, then they're experiencing full strength. The more electronegative they are, they can go ahead and use that as a nucleophile and attack an electrophile. Now, in the best example to show, we have the group 17 of fluorine, chlorine, bromine, and iodine. Because fluorine is the highest on the electronegativity scale amongst these four, in an aprotic solvent, there's no H bond, hydrogen bond, to take away their nucleophiles, so they could all become just in a base form, in an F- form, or in a conjugate base form, right? So they could go and participate in bonding and attacks. But in a protic solvent, there are H bonds, hydrogen bonds, available for it to bind to and make conjugate acids. Because fluorine, the conjugate acid of fluorine, HF, is a weak acid, it is more stable, right? Fluorine is very electronegative, so when it bonds to H, it stabilizes, right? Whereas iodine, when it binds to H, it becomes not as strong, not as weak of an acid, right? So iodine is less affected, so it has more bases in the solution left in the I form rather than HI form than F versus HF form, because F has been taken, it's more receptive to the hydrogen, it's going to get taken up more. So there are more bases available in the I form, or in the basis form for iodine compared to fluoride. Okay, hopefully that makes sense. We have electrophiles now. On the other hand, they are like the receptors for these nucleophiles. They go and attack the electrophile centers. So typically you have carbon cations, especially with the positive on them charge, right? Remember, nucleus has positive charge, and if these are nucleophiles, are electrons, they love the protons. Electrophiles love the electrons, and the electrons will go and attack in the middle. All right, and typically the more bonds and more stable the carbocation is, the more bonds coming off of it, the more stable and the better it is at recepting the nucleophiles. If you see these with double bond, it's also more stable because these can participate in conjugation. Remember conjugation? If we bump this off, electron off, this C becomes positive, and it's a carbocation. Positive and negative, and positive here will be receptive to the nucleophile. Next, we have leaving groups, which are groups that are kicked off, and they're typically weak bases, and they're conjugate of strong acids. So think about the weak bases here. Fluorine is a strong base, but I is a weak base. Right? The stronger the base, the more electronegative it is. So weak bases are typically the conjugates of strong acids, so they're down the periodic table. Now we have two types of nucleophilic substitutions, SN1 versus SN2. SN1 happens because there is one waiting step. In the first step, there is the weak group leaves first and leaves the carbocation there before the nucleophile attacks and joins, whereas SN2, all the steps happen in one, and the nucleophile straight up do a back attack to bump off the original leaving group at the same time as it attaches. So SN1 takes off. Takes off the leaving group first before allowing nucleus and expose it to the nucleophile. SN2 uses both the reaction speed of the nucleophile and the leaving group's ability at the same time. Why it's called SN1? Well, it's only dependent on the leaving group's ability. So that's only dependent on one factor, the leaving group, whereas SN2 requires two factors, the receptibility of this to the nucleophile attack and in addition to the leaving group's leaving ability. Lastly, we have redox, and redox reaction is reduction and oxidation. With oxidation agents such as PCC and chromate and all the multiple oxygen attached to these agents, they help increase bonds to oxygen. Imagine alcohol, right, only has one additional bond to oxygen, but something like carboxylic acid has a lot more bonds to the oxygen. You have a carbonyl group there. So oxidizing agents turn from alcohol up to aldehyde, up to carboxylic acid, and so forth. You can also turn a secondary alcohol into a ketone. Now, reduction works the opposite way. You take away the bonds from the oxygen and reduce them into alcohols, either primary alcohol going this way or you can go into secondary alcohol from a ketone, right? If you reduce a ketone, you turn into a secondary alcohol because the C alpha carbon is attached to 2 additional carbons. Alright, and these are the reducing agents you might see. Lithium with lots of H, and NaBH4 also with a lot of H. So keep in mind, oxidizing agents have a lot of oxygen, reducing agents don't have oxygen, and they typically have hydrogens to help take away the oxygens. Alright, that's it. Good luck.